In this video, we're going to be talking about the interior angle measures of triangles. And even though in this video we're going to focus specifically on triangles, the lesson here is that this is really going to apply to any polygon that we have, because the formula that we're going to be focusing on is this formula here, quantity n minus 2 times 180 degrees, which tells us the total number of degrees inside of a polygon. So all we have to do is plug in for n the number of sides at our polygon. So a triangle is always going to have 3 sides, right? If we plug in 3 for n, because a triangle has 3 sides, we say 3 minus 2 is 1. 1 times 180 is 180. So what this tells us is that the interior angles of a triangle, of which there are always 3, those 3 angles are always going to add up to 180 degrees. So you could do this with squares and rectangles, any quadrilateral, for example. A quadrilateral always has 4 sides, and you'd say 4 minus 2, because there's 4 sides. 4 minus 2 is 2. 2 times 180 is 360. So you know that there are going to be 360 degrees inside of any quadrilateral. So the 4 corners of the quadrilateral are going to have to add up to be 360 degrees, and that's always going to be true. So now that we know that the 3 angles inside of a triangle are always going to have to sum to 180 degrees, we can apply this in a lot of different ways. So for example, sometimes we'll be given a problem like this one, which tells us that the angle measure of angle 1 inside of a triangle is 85 degrees, and the measure of angle 2 is 45 degrees, and then we're asked to find the measure of angle 3. So we know we're dealing with a triangle, and we know that the 3 angles will add up to 180 degrees. So all we have to do is subtract 85 and 45 from 180, and we'll get the measure of angle 3. 85 plus 45 is 130. When I take 130 away from 180, I get 50. So I know that the measure of angle 3 is going to be 50 degrees. So the 3 angles inside this triangle are 85 degrees, 45 degrees, and 50 degrees, and those add up to 180 degrees. Now what about this example here? I have the measure of angle A is 105 degrees, the measure of angle B is 80 degrees. What's the measure of angle C? Well, if I add 105 to 80, I get 185, which is greater than the 180 degrees that we know is the sum of the interior angles. So what I can say is that this triangle here cannot exist because the angles always have to be 180 degrees. This distribution of the 180 degrees inside the triangle is impossible, and this triangle can't exist. What about a problem like this one where we have triangle ABC? We've been told that this interior angle measure here, BAC, or angle A over here, is 40 degrees, and we know that this angle measure outside of the triangle is 140 degrees. We need to find the other 2 interior angle measures of the triangle. Well, how are we going to do that if we only have one of the measures? Over here we had 2 and we found the third. Well, what we need to realize is that the 140 degrees and this angle right here are going to sum to 180 degrees because this ray here, AC, or this line segment AC, is a straight line. So 140 plus whatever this angle is right here has to be 180 degrees because it sits right on top of this line. So if I say 180 minus 140, I can say that this angle here is also going to be 40 degrees because 40 plus 140 is 180. So this is going to be angle measure ACB, which was the first thing I was looking for, so I can say that this is going to be 40 degrees. Now I have 2 of the interior angles of the triangle and I need the third. I know that the 3 together add to 180, so I can say 180 minus the other 2, so 180 minus 40 gets me down to 100, so I can say that this angle here is 100 degrees, which is angle ABC, so I can say angle ABC is 100 degrees, and that's how I can find all 3 angle measures inside of the triangle. And we can even apply this to triangles where we haven't been given any of the interior angles in degrees, but instead we've been given the angle measures as algebraic expressions. So again, I have triangle ABC. I know that the interior angles are going to sum to 180 degrees, so I just have to add each of these algebraic expressions together and set the sum equal to 180. So what I'm going to say is 8x plus 5 plus 4x squared minus 10 plus x squared plus 2x plus 10 is going to be equal to 180, and now I just need to simplify the expression. So we're going to look at our x squared terms first. We have a 4x squared and an x squared here, so we're going to get a total of positive 5x squared, and that's going to take care of these two. Then if we look at our x terms, we have a positive 8x and a positive 2x, so we're going to get a positive 10x, and that'll take care of these two. And then if we look at our constants, we have a positive 5 minus 10, that'll get us to negative 5, and then plus 10 again will get us back to positive 5. The negative 10 and the positive 10 cancel, so we're really just left with this positive 5. So we get plus 5, and just to make sure that takes care of this, and this, we've got everything, and then we're going to set that equal to 180. Now, because every term on both the left and right-hand side of the equation is divisible by 5, we can go ahead and divide out a 5. So if we divide every term by 5, here we're going to get x squared, 10x is going to become 2x, plus 5 is going to become plus 1, and 180 divided by 5 is going to be 36, so we'll get equals 36. If we subtract 36 from both sides, we'll get x squared plus 2x. 1 minus 36 is a negative 35, and 36 minus 36 is going to give us 0. And now we just need to factor the left-hand side. When we do, we'll see that we get this to factor to x plus 7, quantity x plus 7, times quantity x minus 5, equal to 0, and if we set each of these factors equal to 0 individually using the zero theorem, we can say x plus 7 equals 0, so x is equal to negative 7, or x minus 5 equals 0, we get x equals 5. Now these are two possible solutions for x, but what we need to do is plug each of them back into our three algebraic expressions, our three angle measures, to make sure that they are a valid solution. So for example, if we plug x equals negative 7 into this first angle measure here, 8x plus 5 degrees, what we get is 8x plus 5, plugging in negative 7 becomes 8 times negative 7 plus 5, which is a negative 56 plus 5, or a negative 51. So if we plugged negative 7 into this measurement here, we'd get a negative 51 degrees for angle BAC. But that's impossible because all of our angle measures have to be positive, of course, because we're dealing with a three-dimensional figure. So x equals negative 7 can't be a possible result. X equals negative 5 is the only viable result, and if we plug it into all three of these angle measures, what we'll see is that we get a positive result each time, 3 positive angles. So let's go ahead and find the angle measures. If we plug it in here, we're going to get 8 times 5, which is 40, plus 5 is 45, so we get 45 degrees here. If we plug x equals 5 into angle B here, we're going to get 5 squared is 25, times 4 is 100. 100 minus 10 is going to be 90, so we get 90 degrees. And then over here, we're going to get 5 times 5 is 25, plus 2 times 5, or plus 10. So 25 plus 10 is 35. 35 plus 10 is 45. So we get 45 degrees for the measure of angle ACB. Now just to confirm, if I add all three of those together, 90 plus 45 plus 45, I do get 180 degrees. So I double check my result because I know that the three interior angles have to sum to 180 degrees, and this solution that I got, x equals 5, does in fact confirm that these three angle measures sum to 180 degrees. So I know I've done this properly, and I can say x equals 5, I can give a solution for that, and I can give a measurement for angle A, angle B, and angle C. So those are some different ways that you can use the fact that the three interior angles of a triangle sum to 180 degrees to solve some different types of problems about interior angle measures of a triangle.